Hello, everyone. It's Wednesday, which means it's time for a new live stream from Chem Help ASAP. So, in today's live stream, we are going to be working with percent composition, and we're going to be working with it in a couple of different ways. So, the first few problems we will be doing, we will be calculating percent composition given a molecular formula. Then we're going to reverse that. We are going to be given percent composition, and we're going to work back to the empirical and the molecular formula. So let's start with our problems where we're going to calculate percent composition given the molecular formula. Here we go. No, I do not want to exit full screen. So this, you can see these questions are pretty simple. We're just going to calculate the percent composition for calcium oxide. Now, the first thing that we want to do is we want to calculate the molar mass. I trust you guys can do that at this point, so I'm not actually going to write this calculation down. I am just going to give you the molar mass. Okay, so the molar mass of calcium oxide is 56.0774 grams per mole. Now, one reason why I wanted to start with this problem is you think, oh, we've got a compound, it has two atoms, it has two different elements. I bet this is 50-50, right? Half of it's going to be calcium and half of it is going to be oxygen. But that turns out to not be the case because, of course, calcium and oxygen have different molar masses, so they are going to compose a different percent of this molecule. So let's actually calculate what these percentages are. So let's start with the percent calcium because I just tend to move left to right. So for this, what we're going to do is we're going to take the molar mass of calcium of the element, and that is 40.078 grams per mole. We are going to divide that by the molar mass, the total molar mass of the compound, grams per mole. And because this is a percent, we are going to multiply by 100%. So pretty simple, right? And we're going to see very quickly that this compound is not 50% calcium and 50% oxygen. But once we put these numbers in our calculator, we are going to get 71.470% calcium. So this compound is mostly calcium. Again, even if you just look at these numbers here before doing the calculation, you can see that we are not at 50%. So don't be deceived by what the formula looks like. You always want to make sure that you are calculating it using your molar masses. So that is our percent for calcium. Let's go ahead and calculate our percent of oxygen. So we do this in the same way, except this time we are going to use the molar mass of oxygen over the molar mass of the compound. So that is 15.9994. That is the molar mass of oxygen. Again, over our total molar mass, 0.774 grams per mole. And again, times 100%. And we get 28.530% oxygen. Now, when you're doing a percent composition or you have a percent composition, your percentages should add up to give you 100% of the compound. So if I add the 71.470 plus 28.530, I should and I do get 100%. Now, sometimes these percentages will be off by just a little bit, like maybe by 100th or even 1,000th. That's fine. That is going to just be rounding, and that's not a problem. But if you're off, if you're only getting like 90% of your compound, or if you're getting 120% total, then something is definitely off with your math. So this is a very simple calculation for percent composition. And again, it's to highlight, don't let the molecular formula deceive you. It may or may not be 50%. Okay, so, I'm getting a message from OG Benchmarks to turn up the volume. So let me do that very quickly before we move on. So let me find the microphone and bump this up a bit. So hopefully that is a little bit better. It looks like I'm getting a little bit more on the register there. All right, on to our next percent composition. Now, again, we're the first few problems, we're just calculating the percent composition, and then we'll go the other way in just a bit. So this one is we're going to, again, calculate the percent composition. We've got a new molecule. This is actually caffeine, C8H10N4O2. And we want to calculate the percent composition, which means we're going to calculate the percentage of carbon, the percentage of hydrogen, the percentage of nitrogen, and the percentage of oxygen. The first thing we need is the molar mass of caffeine. So our molar mass for caffeine is 194.191. Let me get that decimal a little bit bigger. Of course, that is grams per mole. I generally work left to right. That's just how I do it, but you can choose whichever atom or element that you want to start with first. That's fine. So for our percent carbon, again, we want to take the molar mass of carbon divided by our total molar mass. But the important thing to note here is that we do not have one carbon, but we have 8 carbons. So that becomes a multiplier for our molar mass for that element. I'll show you what I mean. So instead of just having the 12.011, we're going to have 8 times 12.011 grams per mole. Again, this 8 comes from the molecular formula right there. We are still dividing by our total molar mass, 194.191 grams per mole. And we are multiplying by 100%. All right, so if you put all this in your calculator and you hit enter, you are going to get 49.481%. And that is percent carbon. Let's check. Okay, looks like volume is all right at this point. Okay, so that is carbon taken care of. Now let's go ahead and do percent hydrogen. Again, we have another multiplier for our hydrogen. That is going to be our 10. So we are going to have 10 times our molar mass of hydrogen, which is 1.0079 grams per mole. And again, over our total mass for our compound, grams per mole. And finally, times 100%. Sorry, I should put in equals there. Again, putting this into our calculator, we get 5.190% hydrogen. All right, we're halfway there. We still have to do nitrogen and oxygen. So here is our percent nitrogen. So we need to find our multiplier first. We have a 4 right here next to the nitrogen. So this is going to be 4 times our molar mass for nitrogen, which is 14.007. Of course, that is still grams per mole over our total molar mass times 100%. And this gives us 28.852%, and that is percent nitrogen. Now, notice when I'm doing and this is true for any percentage, your units should cancel out. So you can see I'm grams per mole divided by grams per mole, which means my percentage is unitless. That should be true whether you're doing percent composition or you're doing percent yield or you're doing another percent. So make sure your units are matching up here, which is why I always write my units down. Now for our last element, and that is percent oxygen. And I'm going to do this one a little bit differently. So we know that all of our percentages should add up to give us 100%. So when you are on the last one, what you can do is you can add up your percentages here and subtract them from 100. That will give you your percent of, in this case, oxygen. So percent oxygen is going to be 100% minus the addition of all of the percentages we've done before. So that was going to be percent carbon plus percent hydrogen plus percent nitrogen. Okay, so that is simply going to be 100% minus, I'll put all of these numbers in. So carbon is 49.481%. Oh, I'm going to run out of space, aren't I? Hydrogen is 5.190%. And I'm going to have to squeeze this one down here. 28.852%. Okay, so again, once we've got that down, we can put that in our calculator, and we are going to get a percent oxygen of 16.477%. So that is just another way that you can calculate your final percentage. Of course, you can still use the multiplier of 2 multiplied by the molar mass of oxygen divided by your total molar mass, and that will work as well. It's really just up to you which way you want to calculate the final percent composition. Okay, let's make sure that there are no questions. I don't see any questions. Hopefully you're finding these fairly easy, and maybe you just needed a reminder or to see how to use the multipliers, which is why I set up this next problem here, because we have parentheses, so we've got a different kind of multiplier. Again, we are calculating the percent composition, which means we need the percent composition for calcium, nitrogen, and oxygen. Let's get the molar mass first. So our molar mass for calcium nitrate is 164.086 grams per mole. Okay, so starting with our calcium. Now, calcium, you could either think of it as not having a multiplier or having a multiplier of 1, either way. I am just going to write the molar mass of calcium in my numerator without a multiplier. Again, with a lot of these problems, do the way that makes the most sense to you. And of course, we're going to put this over our molar mass for our compound. Grams per mole times 100%. And now we can calculate this. So our percent calcium is 24.425%. Again, that is for calcium. Okay, so that's calcium. Let's go on to nitrogen. So the tricky thing here is you do need to keep track of your multiplier. So of course, there's nothing written next to the n here, but we do have a multiplier outside the parentheses of 2, which means you can think of this as either 2 times the 1 that's assumed to be here, or just multiply by 2. Again, either way, mathematically, they are the same. So this is going to be 2 times our molar mass for nitrogen. Let's make that decimal a little bit bigger. This is grams per mole. And again, over our mass of our compound. 6 grams per mole and times 100%. Okay, we're set. We're ready to put it in our calculator. And we get a percent nitrogen of 17.073% nitrogen. Okay, so again, we're at our last element, so we can either add our calcium and nitrogen and subtract 100, but I kind of want to show the multiplier for this one, so I am going to go through the calculation using the molar masses and not using the percentages, but you're going to get the same answer. So for our multiplier for oxygen, you can see we have a 3 inside of the parentheses, but this 2 is your extra multiplier. So we are going to have 6 total oxygen. That's just simply 3 times 2. So this is going to be 6 times the molar mass for oxygen. That is grams per mole. And this is over 164.086, again, grams per mole times 100%. So when I do that calculation, I get a percent of oxygen of 58.504%. and that is for oxygen. So this is actually a good one to test and show how you might not be exactly at 100%. Sometimes you are and sometimes you aren't, but as long as you're close enough. So if I add up all of my percentages here, since I didn't use the same technique that we used in the previous problem, what I'm going to get is I'm going to get 100.002% for my total. So I am just a smidge over, but it is just a little bit. So I am over by 2/1000ths. That is perfectly fine. That is not a problem. So again, as long as you're getting you should be very, very close to 100. But this little 2 over, do not worry about that. Okay, let's make sure, nope, no questions. So that's great. Now that hopefully we're comfortable with calculating percent composition, we are going to flip the table and we're going to be given percent composition, and we want to work our way back to either the empirical and or the molecular formula. So here is our next problem. Let's make sure I just wanted to make sure that my video feed did not mess up our numbers here. So for this question, it says find the empirical formula for a compound that contains 56.79% carbon, 6.56% hydrogen, 28.37% oxygen, and 8.28% nitrogen. So they are giving us the percent composition. Again, we are trying to find, in this case, we are trying to find the empirical formula. So just as a quick reminder, the difference between empirical formula and molecular formula is your empirical formula is your formula that has your lowest ratio of atoms together. Your molecular formula may match your empirical formula, or it may be a multiplier of your molecular formula. Now, don't worry, in this problem, we are, of course, looking for empirical formula, but we have other problems where we are going to find molecular formula as well. But we're going to start on the simple end. Let's just find empirical formula for this one. So when approaching these problems, one of the easiest things to do mathematically is to assume you have 100 grams of compound. So I'm just going to write this over here. Assume 100 grams of compound. Okay, just want to make sure I didn't write over my face. You do not have to assume 100 grams of compound. You can assume any number of grams of compound. That is completely fine. But 100 is going to take our percentages and just make them into actual numbers. So I'll show you what I mean by this. So we're going to take our calculation for carbon first. So if my compound is 56.79% carbon and I have 100 grams, that means that I have 56.79 grams of carbon. So that's why we assume 100 grams, because it just makes the math really, really easy. Now I'm going to take my grams of carbon and I am going to divide by the molar mass of carbon, and that is 12.011 grams per mole. Okay, and this gives me 4.73 moles of carbon. Now don't worry, we will come back to this, but we need to go ahead and figure out our moles of all of our other elements in this case. So we did carbon, let's go ahead and do hydrogen next. Okay, again, we've assumed we've got 100 grams of compound, which means we have 6.56 grams of hydrogen. I'm going to divide by the molar mass of hydrogen, which will make 1.008 grams per mole. And that is going to give me 6.51 moles of hydrogen. Okay, we're almost there. We've got 2 more to do. Maybe I should say we're halfway there. So that was hydrogen. Now let's do oxygen. Again, assuming 100 grams of compound, we have 28.37 grams of oxygen divided by the molar mass of oxygen, 4 grams per mole, is going to give us 1.77 moles of oxygen. One more to do, and then I'll show you what the next step is. So our last element is nitrogen. So that is going to be 8.28 grams of nitrogen divided by the molar mass of nitrogen, grams per mole. That is going to give us 0.591 moles of nitrogen. Now that I have my moles of each of my elements from my percent composition, what I want to do is identify my smallest number of moles, or maybe to say my fewest moles. And for this problem, that is going to be my nitrogen. It's giving me my smallest number. So I'm going to divide all of my other moles by that smallest number. And I am going to actually do this in green so you can see this is the second step, because when you come back and look at your problems, it kind of looks like everything happened at once. But remember, first you calculated your moles. Now you're dividing by your smallest number of moles. So I am going to divide by 0.591 moles. Again, all of these get divided by 0.591 moles. This one as well. 591 moles, and this one as well. So what we're trying to do at this step is we're trying to find our ratio, our whole number ratio of atoms, because we are not going to write a compound that is, I'll just throw this up here, C4.73, H6.51, etc., etc., etc. That does not exist. We need whole numbers. We know that compounds exist in whole number ratios. You cannot have 4.73 atoms of carbon. That is not possible. So what we're looking for is we're looking for whole numbers, which means when you do these calculations, you should find a number that is very close to a whole number. So, let me switch back to my green. So this ratio here is 8. And it's not necessarily 8 exactly, but it's close enough to 8 that all you need is 8. So this is one of the very few cases where you're not having to worry about sig figs when you're trying to find these whole number ratios. You're just trying to find the whole number. So carbon is 8. When we do this division for hydrogen, we get 11. When we do it for oxygen, we get 3. And of course, nitrogen is automatically 1. And what I'll do, instead of saying equal, I'm going to say approximately equal. Again, you're looking for that whole ratio. So for this 3 here, maybe you got 2.99999. That's fine. You consider that 3. For this 11 here, maybe you got 11.00125. That's fine. Consider it 11. Again, we're looking for that whole number. So now we have our whole number ratios, which means we can write our empirical formula. So this is going to be C8, H11, O3, N. And that is our empirical formula for this compound with these percentages. Hopefully that makes sense, but don't worry, we are going to do some more examples. Let's make sure there are no questions. All right. Time for the next example. So again, we are going to find the empirical formula. This time we've got a compound that contains aluminum at 52.93%, and it also contains oxygen. So we just have 2 compounds. We are still going to assume we've got 100 grams. Again, that just makes the math easier. So assume 100 grams of compound. Just makes the percentages a lot easier. But we have, we're going to have a little bit of a problem. Maybe we'll go ahead and solve for this now. We were only given the percentage of aluminum, but we are going to need the percentage of both of our elements, yes? So how are we going to get the percentage of oxygen? Well, hopefully you're already thinking, wait, my percentages should add up to give me 100%. So if I have aluminum and I need oxygen, I should just subtract 100. And you would be exactly right. So for the percentage of oxygen, this is simply going to be 100% minus 52.93%, which makes our percent oxygen 47.07%. So just as a reminder, sometimes you are given the percentages for all of the elements like we saw in our previous problem, and sometimes you might have to calculate the percentage for the final element. Now that we have both percentages, let's move forward with our calculation to get this empirical formula. So for our aluminum, we are going to take our percentage, assuming 100 grams, which means we have 52.93 grams of aluminum, divided by the molar mass of aluminum, which is 26.982. And that is grams per mole. And that will give us 1.96 moles of aluminum. Now for oxygen, sorry, that decimal really. Okay, so for oxygen, again, we calculated our percentage, but we're assuming 100 grams of compound divided by the molar mass of oxygen, 4 grams per mole. And this gives us 2.94 moles of oxygen. Oh, I forgot my L here. Okay, that's now aluminum instead of just A. Again, I'm looking for my smallest number, which in this case is going to be my moles of aluminum. I'll switch colors just so you can see I'm on my second step. So I'm going to divide each of these by 1.96 to find my whole number ratio. This one is definitely going to be 1. And when you do your oxygen, you get something unusual. Again, you're looking for whole numbers. You should be really, really close to whole numbers, right? But when you do this ratio for oxygen, you get 1.5, which is obviously not close to any whole number. So don't try to round this up to 2. What this 0.5 tells us is that we really have a ratio of 3 halves. Now, again, we're not going to write this compound as aluminum, oxygen, 3 halves. That doesn't work. What we need to do is we need to get rid of that half in the denominator. And the way we do that is we multiply by 2. So now I'm going to take my 1 and multiply by 2, my 3 halves and multiply by 2. So that's going to give me 2 aluminum and 3 oxygen, which means my empirical formula, sorry, not molecular formula, is Al2O3. So again, when you do these ratios, they should be very, very, very close to a whole number. If you get a half, keep that half. It just means you have an additional step. It means you need to multiply through by 2. The other thing I will say is there are 2 other common decimals, and that's for 1/3 and 2/3. So if you get a decimal that is not a 0.5, but is say a 0.333 or a 0.6666, you need to multiply by 3. Because that is, if this was 1/3, that would give you 1. And 2/3 is going to give you 2. So again, it just means you have a fraction as part of your ratio, and you need to get rid of that fraction by multiplying through for the denominator. Okay, any questions about that? No, I think we're good. So just kind of an FYI there on other common decimals that you might see. Let's go on to our next problem. We are determining the molecular formula at this time for a compound that contains 92.26% carbon and the rest is hydrogen. And they give us an extra piece of information. They tell us that the molar mass of the compound is 52.076 grams per mole. Now, the molar mass is something that's critical. We are going to need, but we're not going to need to the very end of the problem. So I still want to first focus on getting the empirical formula first, because I cannot get the molecular formula until I have the empirical formula, which means I'm going to assume that I have 100 grams of compound. So assume 100 grams of compound. Let's start with my carbon. That is going to give me 92.26 grams of carbon. Of course, divided by the molar mass, 12.011 grams per mole, which gives me 7.68 moles of carbon. Okay, let's go on to hydrogen. This is, so we need to calculate. So we just know that the rest is hydrogen, but we don't know the percentage yet. So let's go ahead and calculate that percentage. Again, this is very easy. It is simply going to be 100% minus 92.26%, which gives us 7.74% hydrogen. So again, assuming 100 grams of compound, that means I have 7.74 grams of hydrogen divided by my molar mass of hydrogen, grams per mole, which gives me 7.678 moles of hydrogen. On to my next step, which is where I'm going to find my smallest number and divide by that, which really you could say is either here, but it's actually the hydrogen. So we'll divide by the hydrogen. But you can already see here, without having to put anything in your calculator, these are both going to be 1. They're close enough that they're going to be 1 is equal to 1 is equal to 1, which means my empirical formula is CH. Okay, that's great, but we need to now find the molecular formula. And you can just tell from looking at this that there is no way that this empirical formula gives a molar mass of 52.076. So then the question is this C2H2, C3H3, C20H20? I don't know. We need to find what that multiplier is. So to find what that multiplier, or even you could think of it as a ratio, and maybe we'll think of it as a ratio. What you're going to do is you're going to do the molecular molar mass divided by your empirical molar mass. And again, you're looking for a whole number. So let's put these in. So our molecular formula molar mass, they gave it to us. That is 52.076 grams per mole. Our empirical molar mass, we're going to calculate from our empirical formula, and that I'll write it up here. This is actually 13.02 grams per mole. So that is going to go in my denominator, 2 grams per mole. And when you do this calculation, this is going to give you, again, approximately 4. We're looking for a whole number ratio, which means my molecular formula is C4H4. So you're just going to multiply each of your, well, in this case, it's 1 and 1, by whatever your ratio is. You can also do this by guess and test. So maybe once you've got your empirical formula, you look at your molar mass and you think, I really think I just need to multiply by 2. That's something you can always do. You can always just really quickly calculate a molecular mass if you multiply by 2 instead of actually calculating the ratio. But I find once you get past a ratio of 2, it's just a little bit more difficult to predict. So know that you can always just take the molecular formula molar mass over the empirical formula molar mass, and that will give you your whole number ratio that you're going to use to multiply your empirical formula to get to your molecular formula. And I guess I should make sure that I label this. This is your molecular formula. Okay, again, check for questions. Nope, I'm not seeing any questions. So let's go on to our next problem. Okay, so we've got a compound that contains 21.84% magnesium, 27.84% phosphorus, and oxygen. If the molar mass of the compound is 222.55 grams per mole, what is the molecular formula of the compound? So this is the same deal. This is just a little more complex formula. Instead of just having 2 elements, we have 3 elements. So where our method is going to be exactly the same. We're going to first find the empirical formula, and then we are going to find the molecular formula. So let's, as we have done before, assume 100 grams of compound. And let's go ahead and get our percentage of oxygen. You can see they only gave us our percentage of magnesium and phosphorus. So we need to calculate that percentage of oxygen. And that is pretty easy. It's just going to be 100% minus the sum of our other 2 percentages, plus 27.84%. And so our percent oxygen is 50.32%. Now we're ready to do the rest of our calculations. Magnesium. Okay, taking 21.84 grams of compound divided by the molar mass for magnesium, we get 0.898 moles of magnesium. Let's go on to phosphorus. We have 27.84 grams of phosphorus divided by the molar mass of phosphorus, which is 30.98 grams per mole. And that gives us 0.899 moles of phosphorus. So it's looking like we've definitely got a 1-to-1 ratio here. But we have oxygen still, so we're not finished yet. So 50.32 grams of oxygen divided by its molar mass, 9.4. That is grams per mole, and this gives us 3.145 moles of oxygen. All right, dividing by our smallest number, that is going to be divided by our moles of magnesium, 898 moles, divided by 898 moles, and divided by 898 moles. Okay, so these are, actually that's not even approximately 1, that is just 1. This one is approximately 1. So let me take that off. And for our oxygen, again, we're not getting a straight up whole number. We're getting 3.5. So again, we're getting a half, which means we need to multiply everything through by 2. So this is multiplied by 2, our phosphorus is multiplied by 2, and our oxygen is multiplied by 2. So we have a final ratio for our empirical formula of 2, 2, and 7. So our empirical formula is Mg2P2O7. So now we need to figure out what the molecular formula is. So we need to do our ratio. So we need to find out our molar mass of our empirical formula. So our molar mass of our empirical formula, if you calculate it, you get 222.55. Well, that's a number that we recognize, right? So that is the molecular formula as well. So in this case, our empirical formula is our molecular formula. So I'll just write empirical equals molecular. So what you'll find when you work these problems is sometimes the empirical is the molecular and sometimes it is not. But you always have to be ready for the empirical to be different than the molecular. We have one more problem to do. So let's go through one more calculation. Again, we are determining molecular formula. So this is going to be the same types of calculation. Determine the molecular formula of a compound that contains carbon at 45.90%, hydrogen 2.75%, nitrogen 7.64%, oxygen 26.20%, and sulfur. So the first thing I'm going to do is I'm going to calculate my percent sulfur. So my percent sulfur is going to be 100% minus the sum of all my other ones. So this is 45.90%, 2.75%. Whoops, I got ahead of myself. 7.64%. And lastly, our oxygen. Okay, and this is going to give me a percent sulfur of 17.51% sulfur. Now I have my percentages for all my compounds. I am assuming 100 grams of compound. So let's go through all of these. This one's going to take us a little bit longer just because we have more elements to get through, but again, the calculations are the same. Carbon, 45.90 grams over my molar mass of carbon gives me 3.82 moles of carbon. Going on to hydrogen, 2.75 grams over my molar mass of hydrogen. This gives me 2.73 moles of hydrogen. Next is nitrogen. 7.64 grams of nitrogen over that molar mass, grams per mole, and that gives us 0.546. Okay, nitrogen is done. Now we have oxygen. That is 26.20 grams over its molar mass, 9994. And this gives us 1.64 moles of oxygen. We have one more. We have our sulfur. And that is 17.51 grams of sulfur. That is a 5. Over the molar mass of sulfur, 0.65. I am right here at the bottom of my page. Okay, and this gives us 0.546 moles of sulfur. Okay, switching color. Now I need to find my smallest moles. Okay, so nitrogen or sulfur, it doesn't make a difference. Why don't we just go ahead and call this sulfur? 5, that is again a 546. 0.546. Again, divided by 0.5. Oh, put in an extra 0 there. 546. And again, 546. And our last one that we know is going to be 1. Okay, let's get our ratios. So for carbon, this gives us approximately 7. For hydrogen, this gives us approximately 5. Of course, this is 1. Oxygen is very close to 3. And of course, sulfur is 1. So we didn't have any halves. We didn't have a third or 2/3. Everything worked out for a whole number. So it means that our empirical formula is going to be C7H5NO3S. Let's check its molar mass and see if maybe it is the molecular formula, because this is looking like it might be kind of close. So if you calculate the molar mass of the empirical formula, you get 183.18 grams per mole, which means, again, our empirical formula is our molecular formula for this case. Empirical equals molecular. And in general, I do find that these larger molecules, the empirical does tend to equal the molecular. But again, it doesn't have to. You could have an even larger molecule be the molecular formula. You just need to check your molar masses. So that is it for all of our problems that we're going to work today. As always, if you have questions, if you're watching this live stream after the live stream, you can always leave me a question in the comments. You can contact me by email or Facebook. And again, let me know what you want to see in the next live stream. I'm happy to do any Gen Chem topic that you are working in class or maybe that you have struggled with. Thanks so much for joining us. Bye.